Hello everyone, how are you? I hope you are all doing well. So in today's video, we are going to study the equations of motion in one-dimensional uh, coordinates with the help of numerical method, or we can say the method of calculus. So let us start with the first equation of motion. First equation of motion. So actually, what is the first equation of motion? It tells us about the initial velocity and the final velocity of any object which is moving with the constant acceleration with respect to time. Fine. And we can derive it by using the calculus method and by using the graphical method as well. But here we are going to study that by numerical method or the calculus method. So acceleration can be written as differentiation of velocity with respect to time. That means A equals to dv upon dt. And if we assume if the velocity at time t equals to 0 second is v naught and at t second is v, then we can integrate this equation. So first of all, we have to rearrange the equation. So how to rearrange? Let's cross multiply. So we will get dv equals to a into dt, where dv is the variable. That means the velocity is going to change. And time is also the variable. That means the time is also going to change. But the acceleration needs to be constant, then only uh, we can say that it will be a uniform accelerated motion. So since we are studying here uniform accelerated motion in 1D, so we have to assume that the acceleration is constant. Here, A equals to acceleration and it is constant. Now let's integrate this equation. So what we will get, integrating the equation. So what we will get, we have to put the limits. The velocity is changing from v naught to v. So we have to put the limit as according to that. And then the limit of time, that is from 0 to t seconds. Since we know that here acceleration is constant, so it will come out of the integration. So the equation will be v naught v dv equals to a times 0 to t seconds and dt. And finally, we will get integration as v naught to v equals to a times 0 to t. Since we know that here the dv is the only variable that is going to change, and 1 is multiple of that. And similarly, dt is also the variable, and there is no any other function of time. So that's why we can assume that there is 1 multiplied by dt. So the integration of 1 is the variable itself. That means t. Now let's put the limits. So when we put the limits, we will get v minus v naught equals to a times t minus 0. So finally, we will get the equation v equals to v naught plus at. That is nothing but our first equation of motion, or we can say Newton's first equation of motion. It is Newton's first equation of motion in one dimension. Now we are going to derive the second equation of motion. Second equation of motion. Since we know that second equation of motion can be derived by uh, velocity can be written as, one second, velocity v equals to, it can be written as dx by dt, where x is the displacement in the one direction, or we can say in x direction, and t is the time. So velocity is nothing but it is the uh, time derivative of displacement. So now here also we have to rearrange the equation. So we will get dx equals to v times dt. Fine. And since we know that here velocity is not constant, velocity is changing with time. The constant thing, that is acceleration. So velocity, since from equation 1, since v equals to v naught plus at, so we have to put this in the above equation. So finally we will get dx equals to v naught plus at times dt. Now let us assume that the, we can say the initial position of the object is at the position of the object is x naught. After time t seconds, the position is x. Then the integration will leads us to integrating the equation. So what we will get after integration? Integration will be from x naught to x equals to v naught plus at into dt, and the limit of integration is from 0 to t. Now we will apply the distributive property in the integration. So finally we will get x naught to x dx equals to v naught 0 to t dt plus a 0 to t dt. Fine. So why we are taking v naught outside of the integration? Because it is the constant. Why it is constant? Because it is the initial velocity of the object at time t equals to 0 second. And similarly, acceleration is also constant throughout the motion, so we can take them out of the integration. Now let's integrate them. So finally we will get x minus x naught equals to v naught times t, or we can say v naught times t minus 0 plus a t square by 2 minus 0 square by 2. So finally we will get x minus x naught equals to v naught into t plus half at square. And this is nothing but the second equation of motion. So that's how we have derived these two equations, and now we are going to derive the third equation of motion as well. This is Newton's second equation of motion. Equation of motion in 1D. Now we are going to derive the third equation of motion third equation of motion. What is third equation of motion? Since we know that the acceleration can be written as acceleration A equals to dv by dt. Now let's rearrange this differentiation so we can get our required equation. So it can be written as A equals to dv upon dx into dx upon dt. Fine. Because at the end we can say that dv upon dt is uh, represented as dv upon dx into dx upon dt. From where we can, if you want to go to the original equation, then you can cancel dx to dx and you will get dv by dt. Okay. Now the equation will be changed to A equals to dv by dx. Since dx by dt is the velocity, velocity is dx by dt. Now again rearrange this equation. So finally we will get v times dv equals to a times dx. Okay. Now again integrating this equation, we will get the limit of the v will be from v naught to v naught to v dv equals to, sorry, x naught to x naught to x dx. And why I'm again taking acceleration out of the integration, because we know that acceleration does not depend on the distance traveled by the object. For this particular case only, because acceleration is constant, we have already assumed it is not affected by the distance and it is not affected by the time. So now integrate it. So finally we will get, since the integration of v with respect to dv, it will be v square. So finally we will get v square by 2 minus v naught square by 2 equals to a into x minus x naught. Now let's again rearrange the equation. So we will get v square minus v naught square equals to 2 times a into x minus x naught. And this is the third equation of motion. Newton's third equation of motion. Okay, you might be thinking that why we are taking here x naught, because it is not mandatory that the initial position of the object is always at the origin, or we can say it is always at the zero. So we have to assume a generalized form of the equation. So that's why we are taking here x naught not equals to zero. So if you want to take x naught equals to zero, then you will get your desired equation. So that's what we see in the most of the books. So if at t equals to 0 second, x naught equals to 0 meters, then how the equations will look like. So first equation will be similar, the same equation that we derived. Fine. So first equation will be v equals to v naught plus a into t. And the second equation will become as x equals to v naught into t plus half at square, and the third equation will be v square minus v naught square equals to 2ax. And these are the three equations for motion. They have the lot of uses. I hope this video will help you. And if you have any doubt, then you can ask in the comment section or in the, I'll happy to resolve your doubts.